Good afternoon. Thank you, Phil. I'll be talking about real-time monitoring of fetal well-being via latent processes, and here on the screen are co-authors Tong Chen, Yuhao Liu, our students, and then Cassandra Hazelman, who is sitting in the back, and Djuric, who will join tomorrow. So what I'll be talking about is our dream, how we want to actually monitor the fetal well-being by taking everything we know about the fetus and the mother. So I know that we are here individuals with two different types of backgrounds, at least two, which makes it a lot of fun, so that it is sometimes maybe a little challenging to explain everything so that it's clear to the other side. But I'll try to do it, and I'll have only a few equations, and I'll be very gentle about them when I explain them. So what I will first talk about is how we envision the generative model of the data, or in other words, how it will be mathematically represented. Then I will talk a little bit about the main machinery that we use to make inference about the fetal well-being, and then how we actually do it. So first, what is the generative model? So we think that there is an abstract process that we call WT, and this abstract process is responsible for all the signals that we see. And we can model this abstract process to take values between 0 and 1, where 1 would represent perfectly fine fetus, and 0 is quite the opposite. Then this process WT generates latent processes. Latent processes are somewhat similar to what Phil was talking about earlier today when he was using the variational autoencoder. So these are latent processes that are not observed. And now these latent processes generate another set of processes that can be, for instance, time-varying features. And we can have plenty of those. And these features do not only come from the fetal heart rate or the UA signal, but they can be anything that we know. They can be static, as was mentioned earlier, or they can be dynamic. And now the machine gets this multivariate time series and then has to determine what this WT process is, the fetal well-being. So here is the objective. So use all we know about the generative process and all potentially relevant features to make inference about the process WT. So a little bit of math. So this WT, we represent it as a univariate time series. So that's what it means. WT is in R. In fact, what I said, it is actually in the interval 0, 1. Then XT, this boldface XT, represents the latent processes. And the dimension of these latent processes is the X. And then finally, YT is a vector that represents the observed time series. So T here represents discrete time index, and we just write that this T can take values 0, 1, 2, and so on. So there are a few assumptions that we make, a little bit of math also. So the way how we approach this problem is using the probabilistic framework. So we write probability density functions, and we use these probability density functions to come with the mathematical tools to estimate the fetal well-being. So the first equation shows how the fetal well-being evolves with time. So this is the first equation. So this is a density of WT given the previous values of the well-being. And then the second equation, you can see it's conditional density. XT is a latent process, and it depends on the previous values of the latent process, but also on the fetal well-being, which is very important. And then finally we will have the equation that shows how the latent process affects the observations. So here is a schematic diagram of what I am describing. So W0 is some initial value of the fetal well-being, and then W1 is the value of the process at time instant 1, and W2 the value of the time instant, the value of the fetal well-being at time instant 2, and so on, W3, W4. Here I only show 4 time instants. So then you can see there is an arrow that goes from W1 to X1. So this means that the latent process X1 also depends on W1 as it does depend on X0. So the previous value of the latent process and also the current value of the fetal well-being. And X2 similarly depends on X1 and W2 and so on. And right here, maybe, let's see if I can use this feature. I don't know why it does not work. I don't know. So Y1 depends on X1, Y2 depends on X2. So Y1 depends on W1 through X1, and Y2 depends on W2 through X2, and so on. So this afternoon you'll hear a lot about deep machine learning, and this is also a deep model. We call it deep state space model. So the states are described by these latent processes, X0, X1, X2, X3, X4, and so on. But also there is another process, this W process that is sitting on the top. So here is, again, pictorially description. So this could be one well-being process. You can see the process starts at some value of around 0.6. And then it goes up, and then it goes down. It's a smooth process. Of course, it can be a process that can have abrupt changes. Then this process generates these 2 latent processes, here called X1 and X2. And in principle, these processes may not have physiological interpretation. And then finally, we have these multivariate time series that are observed and that carry information about the most important, the root process, which is the process of fetal well-being. So now a little bit of math. So the first equation that shows Wt as a function of Wt minus 1, so f is a function. We don't know the function. So this is where now machine learning comes in. So this function, how Wt depends on Wt minus 1, is not known. And it is the machine that has to determine what the function is. Similarly, the next equation, xt, that is the latent process xt, that is a function of xt minus 1 and also of Wt minus 1, or Wt. And this function g is also not known. It also has to be determined. And finally, we have yt, the observed process, which has its own function h. It's a function of xt, and it also has to be estimated. So there are many unknowns in this model. But first, let me explain why we work with Gaussian processes. So there is at least several bullet points here, and I will quickly go through them. So the first one is they're capable in modeling complex relationships without assuming specific functional form. So their job is to estimate those functions, the functions that I showed here, f, g, and h. Then they operate within probabilistic framework. So all the results that they provide are probabilistic. So we can tell how sure we are about the estimates. That's very important. Third point, they can handle heterogeneous data. We have lots of heterogeneous data in this space. They can be binary, they can be ordinal, nodes can be converted again to some categorical data, and so on. So GPs can handle them. So they also work within the Bayesian framework, which is very convenient. And finally, they can also work in real time. So in other words, the complexity of the computations will not grow with time. This is very important. So here is how these equations look like when we use these sparse GPs, the ones that we use. And in this equation, again, you can see how now WT depends on WT minus 1, how XT depends on XT minus 1, and how YT depends on XT. So here we have several unknowns. The unknowns are these vectors phi, the matrix psi, and the matrix theta. And the unknowns are, of course, the latent processes XT and the fetal well-being process WT. So two sets of unknowns. The first set of unknowns, the matrices theta, psi, and the vector phi are linear, which is very convenient, whereas WT, XT are nonlinear. So what we do is we have a mechanism to first estimate these linear parameters using Bayesian linear regression, and then for tracking the latent processes we use what is known as particle filtering. So I'll not go into particle filtering, but this is a methodology that can track really these latent processes in time. So here's one example of how this can work. In this example, we have a deep state space process with two layers. The second layer is the one that is the latent process that is closer to the observations, and you can see it is three-dimensional. So these three equations in layer 2 shows how this process can change with time. So these are complicated functions, and the machine doesn't know what these functions are. But this is how they were generated in the example that you will see. Same thing for layer 1. Here for layer 1, we actually have two-dimensional process rather than one as the fetal well-being. So there are two processes in layer 1 and three processes in layer 2. And there are only four multivariate time series. So 4 multivariate time series that will be used to estimate all these latent processes. And here are the results. So on the left, first of all, everything that is in red is the true process. Everything that is in gray is the estimated process. So on the left, the first two curves show how the method can actually track these highest latent two processes. And on the right are the closest three processes to the observations. So we were very happy when we saw these results, and we saw hope that maybe there is something that we could exploit here for the main purpose of tracking the well-being of fetuses. So I would like to conclude with a few thoughts. First of all, deep Gaussian processes hold promise to provide accurate results in monitoring fetal well-being. So this is all conditional. So why I say all conditional? Because everything depends on the quality of the data that we use for tracking. If there is no information there, of course, we cannot hope for much. So we still need lots of work before we start working with real data. And there we will, of course, have to collaborate with people on the other side, which is how to calibrate the model so that it knows what is well-being of that takes value of 1 and what is a well-being that takes a value of 0. So the method can also be used to determine which of the use features in the process are important and which are not. This is very nice capability. In fact, we can go even as far as to say how much these features contribute to what we see, to the well-being of the process. So we can split from 0 to 1, and we say 30% comes from this feature, 20% comes from that feature, and these features also, these attributions vary with time. This is this fourth bullet, and then the model can also be used to recommend medical interventions. This is another important thing. So I'm not sure how many of you, those who are in the machine learning world, have worked on Bayesian optimization. So Bayesian optimization is a methodology that is used to, for example, design experiments, or to simply find what is the best argument that can maximize an outcome. So when you define the reward as maybe the state at which you want to see the fetus, then, and you have a library of interventions, you can then choose the best one that will bring the fetus from, say, a poor state to something that is desirable. So this is one other potential application of this methodology. And I'll stop here. Thank you.